The other important component of a modern file system is a mechanism for users to organize files into directories. However, there is a common misconception about directories. Many students think that a directory is like a space, a disk space, that holds the data of their files. This is not true. The data of your files are stored elsewhere outside of the directories. The image on the right is chosen to emphasize the idea that a directory is just a pointer that will guide you to a specific destination. In our case, the destination is a file. The signpost in the picture tells you which direction to take to go to Vancouver, Los Angeles, and so on. So the city of Los Angeles itself is not in the directory. The city of Los Angeles is outside of the signpost. Let's use a different illustration that closely resembles how directories are organized. In a shopping mall, you may find a directory board that helps you to find a particular store. Each directory entry is simply a pair of business name or store name and its location. A directory in a file system is organized in the same way. Each directory entry in a file system is simply a pair of file name and their location, their physical location in your drive. Besides business name or file name in a directory entry, you may also see some other metadata. So for instance, with a store, it can tell whether the store is a health provider or home appliances or food court or something else. So just remember this idea that a city directory holds only the city name. Same thing with a file directory. A file directory holds only the file name and potentially other metadata of the file, like the size, the location, the owner, the type, whether it is a binary or text file, and so on. The most common structure of a directory is typically a tree structure and multi-level subdirectories. A directory is simply a file with a special content. Instead of storing the ASCII characters of your C code or binary data of your JPEG image, a directory entry is just a pair of string and integer. The string is actually the file name or directory name, and the integer is the physical location where to find your C code or your JPEG image on the disk. In this illustration, green boxes are directories and yellow boxes are regular files. The root directory has 3 entries. The first entry is a file, the second entry is a directory, and the third entry is also a directory. It is very common for you to share your data or files with someone else in the system. Let's say 2 developers, Adam and Beth, are working on a common project and they both need to access a common data file. Adam is currently the person who holds the data and he wants to share the data with Beth. So Adam can take one of the following 2 actions. So the first action, Adam can attach a copy of the file to an email and then send the email to Beth. Or the second action, Adam can just send the URL to the file and then just send the URL to Beth, and then Beth can then later access that file from her Google Drive entry, let's say. So using the second approach, we will see that only one copy will exist in the Google Drive, but then both developers can access to the same copy of the file. So this is why linking or file linking is an important feature and useful feature in a file system. A link in a directory is just a pointer that leads to the actual file. The 2 pictures in this page show 2 signposts that direct you to the city of Los Angeles. Although you see 2 pointers, but there is only one city of Los Angeles. Creating a link in a file system is simply to create a new directory entry without creating the actual data of the file. In this illustration, let's say you create a file, syllabus PDF, under the courses directory. When you create that file, the file system will perform the following two actions. First, it will allocate disk blocks to hold the PDF file, and then second, it will create a new directory entry to hold a pointer to that file and other metadata of the file like the file size, the creation date, the owner, and so on. Now let's say the next day you decide to reorganize your files into a different structure, and then now let's say you want to see the same file to show up under your work subdirectory. Instead of making a second copy of the file, what you can do is just to make a link to the same file in your work subdirectory. In this case, the file system will perform only one action to create a new directory entry under the work subdirectory and then copy the metadata found in the other directory entry to that directory entry. So practically, no new disk block will be allocated to create the second entry in your work subdirectory. So as with files, the file system should provide basic operations to manipulate your directories. So the typical CRUD operations will be to create a new directory after you create a file and to read the content of the directory, or to update. Maybe you want to change the name of the file, or you want to change the owner of the file or the group owner of the file. And of course, when you don't need that file anymore, you will be deleting that entry from the directory. Linux provides two kinds of file linking, hard links and soft links. Hard links are created in actually one step. So the system will just create a new directory entry by copying metadata of the source file S. So this idea is similar to having multiple directory boards in a mall, and you may see multiple boards that point to the same store location. But symbolic links are created in two steps. So the first step, so let's say we are going to create a symbolic link to a file S. So the first step is for the system to create a new file, let's call it T, whose content is the path to the source file S. And then the second step, the file system will create a new directory entry for T. So now you can think in Linux, a symbolic link is like a pointer to a file. Let's use a live demo on a Linux machine to see how hard links and soft links are created. I'll be using this file as my example. So the file name is gvsemaphore.cpp. The file was created back in 2017 and the file size is 737. So I'm going to run a script. The script will guide us step by step through making a hard links and then inspect the details of the hard links. So first, it shows you the details of the current file, the file size, and the inode. So what is an inode? An inode in Linux is a data structure associated with each directory entry. So for one directory entry in the file system, Linux will be using one inode block. So the inode number is shown here, and links is the count of how many directory entries associated with our file. And the next three lines show you the three different timestamps. So the first timestamp is the last access time, and the second timestamp is the content modification, and then the third timestamp is the update to our metadata. We are going to create two hard links. So the first hard link will be called a_sem_cpp, and the second hard link will be called b_sem.cpp. So now we have two hard links and the original file. Now if you look at the details of these files, you will see that all of them will have the same size, the same inode 992.1920, and the same link counts, also the same timestamps for all of them. So essentially, hard links are multiple directory entries pointing to the same file. Essentially, when hard links are created, the file system will copy the metadata from the input file to create two new directory entries for b, sem, and asem. Now, what if I remove one of the files? So let's say if I remove a_sem.cpp, what will happen? So this is the details after we remove one of the directory entries. We have only two files, gv_semaphore.cpp and b_sem.cpp. As you can see the details. The inode of the two are the same, but now the link counts goes down from 3 to 2. Why is that? Because now we have only two entries, two directory entries pointing to the same file. Now how about for a soft link? So if I run the same demo again, but now for a soft link, I'll be using the same file again. So the same input file, gv_semaphore.cpp with that size and with the inode. And currently the link is only one. And we create two soft links. The first soft link will be called asem.cpp, but the difference now, I'm using this extra flag -s to tell the system that I'm creating a soft link, not a hard link. And the second soft link is created using the same name, b_sem.cpp. And if you inspect the details of our soft links, you will see that the three links are technically three separate directory entries. And the link count for each of them is 1. A disk can be typically organized into one or more partitions, and that's why you do need to have a partition table. Currently, there are two partition formats that are used in modern computers today. The first one, the old one, is what we know as MBR partition, Master Boot Records partition. With the MBR partition, your disk can be partitioned only up to 4 partitions. And the newer format is the GPT partition. And with GPT, you can have as many as 128 partitions in your hard drive. Having multiple partitions allow you to install several different operating systems on the same hard disk. So for instance, in the first partition, you can format that partition using VFAT to install Windows, and maybe on the second partition, you can format that using ext4 file system to install Linux. And finally, modern operating system also gives you a feature that will let you organize several physical drives into one logical volume. So in this example, you see physically your computer may have 3 separate physical drives of different capacity. So let's say disk number 1 has a capacity of 500 plus terabyte, the second disk has a capacity of 200 plus terabyte, and the third one has a capacity of 300 terabytes. Instead of working with individual drives separately, a modern file system may give you a feature that will combine the 3 physical drives into one logical volume. So in this example, instead of having like 3 separate drives, the system may give you an illusion that you have a bigger drive of bigger capacity. So technically, if we combine the capacity of the 3 drives, then we can get a logical volume of size up to 1 petabyte. And the other concept that are commonly used in a file system is the idea of mounting. Historically, when mainframe computers are popular, mainframe operators must mount or unmount magnetic tape to a tape drive in order for the computer to read or write data. But today, you have seen this in practice whenever you insert a USB drive to your computer. So technically, when you plug in your USB drive, you are mounting the USB drive to the computer, and when you eject the USB drive, you are unmounting the USB drive from your computer. So in this page, you see the actual output from our EOS machine. From the output of DF on this page, you can actually see that the home directory of all users is mounted from a remote location, and the IP address of that server is here. And the other subdirectory mounted from the same server is the lab groups multimedia. And you see numbers from the output. So the first number is the total disk space on that partition, and the second number is how many bytes are used, and then the third number is the number of bytes available for user to use.